This video is going to cover sections 10.2 and 10.3. In section 10.2, now we're going to talk about the strengths of acids and bases. Table 10.3 in your textbooks has a list of the common strong and weak acids. By definition, a strong acid is going to be a substance that completely ionizes in aqueous solution. So if we relate this to concepts that we explored in chapter 9, strong acids are going to be considered strong electrolytes. Weak acids are going to be substances that are going to dissociate slightly in water to form a few ions in aqueous solutions. So weak acids, if we relate it to the concept of electrolytes, are going to be considered weak electrolytes. In order to know what makes something a strong acid and a strong base, a strong acid versus a weak acid, is better that we just know what are the 6 strong acids in anything that is not in that 6 strong acid list, then it is considered a weak acid. So, as you can see, the 6 strong acids that you guys have are hydroiodic acid, hydrobromic acid, perchloric acid, hydrochloric acid, sulfuric acid, and nitric acid. Any acid that is not part of those 6 strong acids, they are considered weak acids. When it comes to bases, understand that strong bases are going to completely dissociate in water. So when it comes to strong bases, they are also known as strong electrolytes. Now, how do we know that a particular base is a strong base? Well, as you can see, strong bases are going to be formed from metals that are part of group 1A and group 2A, and they are going to be paired with hydroxides. Note that the only other base that does not contain hydroxide, and we discussed so far in the lecture, is NH3. And because NH3 does not have a hydroxide, that's why it's considered a weak base. In section 10.3, now we're going to talk about how acids and bases form equilibrium systems. So when it comes to an equilibrium system, you know that a system has reached equilibrium because there are no further changes in the concentrations of reactants and products, and the rate of the reaction for the forward reaction is equal to the rate of the reaction that is happening in reverse. We illustrate this forward and reverse reactions by either doing double-headed arrows or by doing arrows in both directions. So those are the 2 ways that we illustrate them. So here you have an example of a reaction in equilibrium, which is hydrofluoric acid reacting with water, forming fluoride and hydronium. So this H3O plus, even though is in the table in the previous slide, this is called hydronium. Specifically hydronium ion, because as you can see, it has a positive charge. Whenever we're talking about equilibrium systems, we need to discuss Le Chateliers Principle, because Le Chateliers Principle states that when a system is disturbed, the rates of the forward and reverse reaction are going to change to relieve the stress and reestablish equilibrium in the system. So what that means is that if we alter the concentration of reactant or product of a system, remember the rates of the reaction in the forward and reverse directions are not going to be equal. So they are going to do some changes in order for the system to reestablish that equilibrium. Okay, so every time we change amount of products and an amount of reactants by adding or removing, that creates a stress in an equilibrium system. In order to understand Le Chatelier's principle, I like to utilize the analogy of a water tank. As you can see, the tank overall has two compartments, the tank A and tank B. So the water appears on the first system to be at equilibrium. As you can see, if we increase the amount of water on tank A, that means that we're going to see an increase in the way that that water is going to rush towards the right. So that means that in order for the system to regain equilibrium, as you can see at the end, so this is going to be what the stress that has been added, and number 3 is how the system regains equilibrium. The water is going to rush towards the right. So how is this related to Le Chatelier's principle? Let's assume that tank A is going to represent the reactants in a reaction. And tank B is going to be talking about the products of a reaction. So in this system, if we relate it to a chemical reaction, as we're adding more reactants, aka adding more water on tank A, the water is going to rush towards B, meaning increasing the rate of the forward reaction so the system regains equilibrium. Okay? These observations that summarize Le Chatelier's principle are all present in table 10.4. But instead of going through them one by one, I am going to go over the worksheet that specifically has problems where we can illustrate how the Le Chatelier's principle is at work in an equilibrium reaction. So on part E of the worksheet, as you can see, we have two problems. I am specifically going to go through the first one. And this problem reads, what will happen to the position of the equilibrium when the following changes are made to the equilibrium system below? In this equilibrium system, as you guys can see, that reaction is a decomposition reaction. We have sulfur trioxide being converted to sulfur dioxide and molecular oxygen. So we are going to be talking about the different stresses that we're doing to the system. For this, you need to know how to name each one of those compounds. So on the first instance, as you can see, we have sulfur dioxide being added to the system. Sulfur dioxide is this compound. That compound is present in the product side. Since it says that sulfur dioxide is added to the system, we are going to be adding product of to the system. So this means that in order for the system to regain equilibrium, we are going to be increasing the reverse reaction, meaning that this arrow is going to be pointing towards the left, meaning towards the reactants. In the second situation, we have sulfur trioxide being removed from the system. Sulfur trioxide is going to be this compound. As the second statement mentions, we are going to be removing the reactant from the system. So when that happens, understand that this is going to decrease the rate of the forward reaction, and the direction in which this shift is going to happen is still towards reactants. Let's talk about the last system, which is oxygen is being added to the system. So as you can see, oxygen is being added to the system. When this occurs, remember, oxygen is going to be in the product side. So here is going to be similar to statement A. So we are adding product, which means that we're going to increase the rate of the reverse reaction, which means that in this case, the direction in which this equilibrium reaction is going to shift is going to be, again, towards reactants. So statements A and C have the same effects on this equilibrium system.